Numerical simulation of shock wave effects on ship-like form. Here is content. Powerful underwater blasts that threaten the combat survivability of the Navy ships or submarines are a major security concern. Impact of a shock wave on a sea vessel may cause severe structural and equipment damage, besides personal injuries and casualties. Therefore, naval ships must be shock hardened as much as possible to ensure combat survivability for both personnel and equipment. The most reliable way of testing a ship for survivability is to conduct shock trials. However, with extensive planning and coordination, such a trial may take a year or more. Furthermore, environmental lawsuits can cause the delay or even cancellation of the trials. And an actual trial involving underwater explosion can destroy the tested military vessel completely. For all these reasons, realistic combat testing of military vessels is quite difficult. On the other hand, predicting structural response of a submerged or surface vessel to underwater shock waves is a study subject whose outcome is much sought by naval engineers. To this end, numerical simulations offer an alternative for studying structural responses and assessing effects of underwater blasts. So we try to analyze shock effects on ship-like form with 3 numerical simulations. An ALAE code is used for the simulations of shock wave effects on a ship-like structure. Structural deformations observed from the hydro code simulations are correlated with the corresponding TSF values for formulating a simple expression to estimate the extent of damage quantitatively. Basically, linear dependency of the maximum permanent deformation of TSF, though observed for limited data, established as a confidence on the reliability of TSF as a simple criterion estimating the extent of damage due to underwater blast. We try to analyze the structural response to index. Numerical simulations using the software Elestina require the specifications of definite components, so we model explosive, fluid, air, and structure. The ship geometry is modeled as a box-like barge structure of length 42 meters and beam 8.75 meters with appropriate longitudinal and transverse structural components and 2 bulkheads. The total weight of the structure is represented as 3 lumped masses of 370 tons, evenly placed along the keel line, ensuring that the center of gravity corresponded to amidships. Shell plating is specified as 0.2% sea-hardened steel of 7 mm thickness. The structural steel parameters used in the simulations correspond to the steel commercially called DH36. We know that mechanical and thermomechanical tests performed on DH36. A first simulation data are on screen. We use 500 kilogram explosive TNT equivalent. The second simulation is similar to first simulations, just different of weights of explosive. The second simulation, we use 1000 kilogram TNT equivalent. The third simulations are similar to second simulations, but the location of the explosive is just underneath the ship. So the theta is equal 1. Sinus theta equal 1. In order to observe certain location on the ship hull, 8 specific nodes on the bottom of the model were selected. Here are the nodes. At these 8 nodes, simulating data were recorded using the database history node command. This particular feature is crucial in obtaining the structural displacement, velocities, and accelerations at selected locations. We use 5 different kinds of beam elements. Sorry. 3 different sizes of stiffness, transverse elements, fine steel plates, 5 millimeter and 7 millimeter thickness. These are used as shell elements covering the box-like form. Every simulation took approximately 10 days. Here you can see shock wave effect on the ship-like form in the third simulation. Here are the data of all 3 simulations. Here are the displacements of first simulation, velocity of first simulation, accelerations of first simulation, displacements of second simulation, velocities of second simulation, accelerations of second simulation, displacements of third simulation, velocities of third simulation, accelerations of third simulations. The maximum displacement values as average for all 8 nodes for simulations 1, 2, and 3 are found to be approximately 37.8 centimeter 56.6 centimeter and 90.8 centimeters, respectively. The computed deformation for simulation 3 is obviously too large for the material to withstand without breaking, hence it should be viewed with caution. Effects of a 3D underwater explosion on a box-like structure representing a ship beam are investigated through numerical simulations by employing the software LS-Line with the ALE approach. 3 different simulations are performed to explore the effects of various in KSF. The second simulation, designed for KSF almost equal with 1, represented a case for which the field measurements were available through not open to general use. With the use of limited simulation data, a linear relation between the maximum deformation and the corresponding KSF values is established. So, 3 different simulations are performed to explore the effects of variations in KSF. With the use of limited simulating data, a linear relation between the maximum deformation and the corresponding KSF values is established. Considering the calculated kickoff velocities for KSF equal 1 series, but for KSF larger than 1, fatal damage to ship-like structures appears certain. Thank you. I'm ready to answer your questions and comments.
Thank you. Also, maybe we should clarify a little about this KSF. I didn't notice if you have defined it there, but KSF is a measure of actual damage established through the years. So it means it is related to the explosive mass and the distance and the angle of the explosion taking place with respect to the keel of the ship. So it seems, I mean, from there, if I may contribute to the conclusions, it seems that KSF is a good measure to estimate the damage. At least it can tell us that if there will be a serious damage or even a devastating one, from the beginning we can make an estimate as to the extent of the damage. I just want to clarify this as an advisor to Colonel Tatlisuluoglu in this work. But we can take, of course, any other questions and comments.
Yes, thank you.
Thank you very
sir.
much.